Good afternoon.
Hi. How are you doing?
Okay. How you?
Good, good. How was your weekend?
Full of deadlines.
That's how it should be. Students are busy. But be well trained to deal with them because there will be more of them in future. Okay. Hi guys, nice to see you. So just short remind what we considered last lecture. Hello everyone. Hello. We introduced the concept of capacitance, which is some feature of isolated bodies or systems of two conductors to accumulate electric charge. So it shows how much the potential of the surface of these conductors will change by increasing the accumulated charge by certain coulomb. Like 1 farad is stands for increase in the potential difference between two plates of a capacitor by 1 voltage by 1 volt, and in that case when we accumulate 1 coulomb of electric charge. So we considered how to calculate capacitance of isolated sphere or parallel plate capacitor, also considered other types of capacitors like some cylindrical and spherical capacitors, and considered what will happen if we connect these capacitors in parallel. So how we calculate the equivalent electric capacitance of a battery of capacitors connected in parallel. So today we continue with the consideration of series connection of capacitors. And once we are done with that, we will go for quantifying potential energy which is accumulated in capacitors when they are charged. So this is our plan for today. Let me change the camera and proceed with the series connection of two capacitors. So let us consider two capacitors connected in series. So we have C1, C2, also delta V1 and delta V3. So keep in mind that initially these capacitors are not charged. So there are no charges on the plates of these capacitors. And then we connect it to some battery, like some DC power source, plus minus. So as a result, we will start to charge the plates of the capacitors. And we know that, for instance, we have here minus Q1. So on the opposite side, it should be plus Q1. The same from the right. Here we have plus Q2, and here we have minus Q2. Now, pay your attention to the fact that only external plates are connected to the power supply, to the battery. And that's only those plates which can participate in the charge transport via the wires and battery from one plate to another. At the same time, the two internal plates are not connected to anything. They are isolated from this electric circuit by these gaps between plates. So initially they were electrically neutral, and only because of reorganization, like rearrangement of electric charges, which already exist in these plates, and this wire which connects the plates, we build up electric charges Q minus Q2 at the right side and plus Q1 at the left side. Since initially this isolated system of two plates was electrically neutral, and we didn't have any opportunity to bring charges or extract charges from this system from external environment, means that it should remain electrically neutral in total. It's just we have these charges only because of rearrangement of electrons. They are moved to the right, so we accumulate some net negative charge minus Q2 and residual positive ions in the crystalline lattice of this metal, which forms plates. They form some net charge plus Q1 at the left side. Since this system should remain electrically neutral, we can write that by absolute value. Oops. Q1 is equal to Q2. And then we can claim that electric charge, which is accumulated in capacitor 1 and capacitor 2, is the same. So we will operate with some charge Q. Since we know now that electric charges which are accumulated in capacitors connected in series are equal, so each capacitor in this sequence of seriously connected capacitors accumulates the same amount of electric charge, we can proceed further. So we know that total difference, potential difference, will be delta V. It's defined by our battery or power source. And we can write that total potential difference at the electrodes of this battery of two capacitors connected in series will be equal to the charge which is accumulated by the system of capacitors divided by some equivalent capacitance of this battery. The same we can write for the rest of, like for separate capacitors, but there we will use respective voltage, like potential difference between plates. For first capacitor, it will be delta V1 will be equal to Q divided by C1, which is capacitance of the first capacitor. Also, delta V2 will be equal to Q divided by C2. We know that total potential difference in our case will be split in two components, which is potential difference at between the plates of the first capacitor plus potential difference between the plates of the second capacitor. So from here, by substituting expressions for each of these potential difference, which we defined earlier, we can write that Q divided by C equivalent is equal to Q divided by C1 plus Q divided by C2. Here we cancel out this Q because it's the same for all cases, and end up with familiar equation that 1 over equivalent capacitance is equal to the sum of reciprocal to capacitance of each of the capacitors which are connected in series, C2. So we can now extend this to the larger number of connected in series capacitance. Let's say we have some N capacitors connected in series, and when we want to determine equivalent capacitance, then we need to sum from I equal to unity to N 1 over Ci. So this is the way how we calculate equivalent capacitance of capacitors connected in series. So what is important here, if we compare with the similar equation which we derived for the parallel connection of capacitors, it was C equivalent equal to sum from I equal to 1 to N Ci. So it means that by adding more capacitors which are connected in parallel, we increase equivalent capacitance, and by adding more capacitors which are connected in series, we decrease equivalent capacitance, and moreover, it always will result in smaller equivalent capacitance will be always smaller than the smallest capacitor in this battery, which consists of capacitors connected in series. So this should be taken into account, and then you can deal with different combinations of series and parallel connections of capacitors. So what you need to do, you always should have to define segments of electric circuit where you have clearly noticed the type of connectors for limited number of capacitors. Calculate this local effective equivalent capacitance, and then calculate equivalent capacitance of the battery of this equivalent capacitors. So by doing with this sequence, simplifying the electric circuit, you can eventually come to a single equivalent capacitance of all complicated battery of mixed connections of capacitors, where you can see series and parallel connections simultaneously. So now we proceed further, and need to consider energy storage in charged capacitors. So because we have some positive and negative charges separated in a capacitor, so there is some internal electric field between the plates of the capacitor. We accumulate certain potential energy in electrically charged capacitor. So let us try to quantify what it will be. So first of all, let us consider some small work which should be done by charging a capacitor which is at potential difference delta V by adding some small electric charge dq. So we know that this potential difference can be represented as a charge which is already, like previously, accumulated at the plates of the capacitor divided by the capacitance of this capacitor, and that times dq. So now if we want to consider some defined electric charge, which we want to add to the system of two plates, which we call a capacitor. Let's say this is some charge Q capital. And then in order to calculate work, which has to be done for charging such a capacitor, we need to integrate this last equation in the range from 0. Let's say if we charge our capacitor from 0 to this charge Q. So total work will be integral from 0 to Q over C dQ. So we know that, do we know? Let's check. What do you think? Does capacitance C of this capacitor depend on electric charge which is accumulated on the plates or not? Who has any ideas?
Sorry, can you repeat the question?
What do you think? Will be certain dependence between capacitance C in this integral and electric charge Q accumulated in capacitor? Because it will define either we keep this C in the integral because it's a function of Q, or we can take it out from the integral as a constant if it doesn't depend. So what is the factor which defines capacitance of any capacitor? It's geometry. So it doesn't matter what is the potential of plates of the capacitor, what is the difference of potential between them, means there is no dependence between capacitance and electric charge accumulated in the capacitor. There's only one factor, is geometry of these plates, what defines the ability of the capacitor to accumulate charges. For instance, if we have a parallel plate capacitor, equation for the capacitance, epsilon 0 times A divided by D. Here we don't see any charge or potential difference. what parameters? Epsilon 0 is permittivity of free space, it's just fundamental constant. Then we have area of capacitor plates and distance between these two plates. So that's why only geometry of the system of two plates defines capacitance. In this case, we know that capacitance is not a function of accumulated electric charge, and for this integral, it's a constant. So we can take it out like from this integral, and we have Q times dq. Okay. So keep this in mind, that there is only geometrical factor which defines capacitance of a single conductor or system of two plates, which is like two conductors, which we call a capacitor. Doesn't matter what is the type of capacitor, only geometry defines its capacitance. So with this integral, we get Q squared divided by 2, and this will be from 0 to Q. So we will end up with Q squared divided by 2C. So this is the work which has to be done to charge some capacitor with capacitance C with electric charge Q capital. And now we can think a bit in the reverse, that if we need to do certain work to charge this capacitor, means that that would be accumulation of certain potential energy inside this capacitor, which is equal to the work which has to be done to charge it to a certain level. So because this energy, like this energy conservation should work. If we perform some work, this work should be converted in some type of energy, either potential or kinetic. Since nothing is moving inside the capacitor, we accumulate energy in the form of potential energy, which is equal to like minus work which is done. So in this case, we can write that potential energy accumulated in this capacitor will be Q squared divided by C, the same as work done to charge this capacitor. And now we need to take into account the relationship for which defines capacitance. So we know by definition that capacitance is electric charge accumulated divided by potential difference between the plates of the capacitor. So we can write here like this: Q divided by 2 times Q divided by C. And Q divided by C from this definition of capacitance will be potential difference, Q divided by C. So we can write Q times delta V divided by 2. And finally, we can also express this Q, again from this definition of capacitance. Q is can be expressed as capacitance times delta V. So now if we substitute here Q by its expression C times delta V, we end up with the most common equation for the potential energy accumulated in the capacitor as 1/2 times C capacitance times delta V squared. So this is kind of one of the most common form, but also like these forms are obviously also valid and can be used. So let us show it graphically for better perception of this information. Let's plot delta V here, axis, and here will be charge accumulated, Q. So if we increase from 0 to certain charge Q, accumulated charge at the plates of the capacitor, the potential difference between plates of the capacitor will linearly increase with the increase of accumulated electric charge. So this slope of this linear dependence, here we have delta V, and here we have delta Q, or like this, delta Q. This slope, it will be 1/C. So it will be, the slope will be defined by the capacitance of the system, delta U divided by delta V. And the work which has to be done to charge this capacitor from 0 to Q, and as a result also potential energy which is accumulated inside the capacitor, will be equal to the area under this linear dependence. And we have shown on the previous slide that this potential energy is equal to 1/2 C times delta V squared, and that was obtained from the previous form, which was 1/2 Q times delta V. So we see that Q is here, it's this side of rectangular. This is another side, delta V. So Q times delta V is area of this rectangular, and if we divide it by 2, it will be area of this triangular, which is dashed. So it will be area under the linear dependence between delta, like potential difference, and accumulated charge in the capacitor. So this is definition of potential energy accumulated in electric capacitor. And now let's go step forward and understand in which form it's accumulated and what is some specific characteristic of this accumulated energy. So obviously, as I mentioned, there's no moving parts in the electric capacitor, just 2 plates, stationary. We perform some work, like external agent performs some work to charge capacitor, and this energy is accumulated in the form of potential energy, but this potential energy is actually energy of electric field, which is created between the plates of the capacitor. And now let us calculate the relationship between accumulated potential energy and electric field between the plates. So we know that, yeah, let's maybe show here two parallel plates, plus, minus. We have certain uniform, assuming that we have large plates, much larger than the distance between the plates, uniform electric field inside this capacitor. And this is a substance which actually accumulates this, represents this potential energy accumulated in charged electric capacitor. So let's say for such a parallel plate capacitor, assuming uniform electric field, we can write that change, like difference, potential difference between the plates is equal to this uniform electric field times d, the distance between the plates. And also, we already on previous lectures derived equation for the parallel plate capacitor, which, by the way, you should remember very well. It is epsilon 0 times A divided by D. So we have expressions for potential difference in capacitance specifically for the case of a parallel plate capacitor, assuming the uniform electric field between the plates. And now let us substitute these parameters here in this equation for the potential energy. So what do we get? It will be potential energy is equal to 1/2 times C, and C is epsilon 0 A over D, times delta V squared. And this is E squared times D squared. So now we can a bit, so we cancel out this D and square here and a bit rearrange this expression. So we have 1/2 epsilon 0 A times D times E squared. So we see from this equation that the energy of electric field is defined by the square of the magnitude of electric field vector, E. So we have dependence, like square dependence between the potential energy in certain point of electric field on the strength of electric field in this point, like magnitude of the electric field vector. This is very important concept. You need to also be aware of this, that there is a square dependence between accumulated energy, like potential energy of electric field and electric field vector. So another step, what we can do, we can consider some specific characteristic, because so this particular case is valid for parallel plate capacitor because it's based on this geometry, which is defined by two parallel plates. However, if we want to derive some general equation, which is valid for any electric field created between any random shape plates or created by some point charge, then we need to get so-called specific potential energy of electric field, which is normalized to per unit volume. So in this case, in the expression here in parentheses is the product of universal constant permittivity of free space. And here, like this, A times D is the volume which electric field occupies between two plates. So it's area times distance between plates. So that's why if we divide this expression by area, we will get the general expression for the energy per unit volume of electric field. So this is shown as UE equal to this capital U divided by area. And in this particular case, we have A times D. So we will end up with this equation, 1 over 2 times epsilon 0 times E squared. So this is true for any electric field. So now we are not attached to certain geometry. If we have electric field specified in the space as a vector field, then we know that in any unit volume of this electric field, we have certain energy due to the existence of electric field, which is UE, and this potential, this like energy in this unit volume is proportional to the square of electric field vector in this given point. So obviously, if we have non-uniform electric field, we need to divide this volume where we consider electric field like in very small volumes where electric field can be considered as uniform, and then calculate this specific characteristic energy per unit volume of electric field in this point of space. So this is the concept of energy of electric field and its dependence on the magnitude of electric field vector. Keep in mind that this is quite interesting also for practical application, accumulation of energy in capacitors. And for instance, you all should know such like bolide racing like competition where cars should weigh very as little as possible, and in order to reach the highest possible speeds. So obviously it's not possible to use regular acid lead capacitors, like not capacitors, but accumulators, which are commonly used in regular cars to start engine. That is the main purpose of at the initial moment when you need to start your car, you need to rotate the engine and you use the energy accumulated in electric accumulator. Usually they are made of lead and filled with acid, and they are very heavy. Definitely not appropriate approach for some sport cars. And that's where capacitors replace these accumulators. So one of the unique feature of capacitors is internal resistance approaches to zero, because we have just metal plates, and their resistance is very small. So we don't have any internal resistance, and that's why they can provide for very short time, can be discharged and provide very large current. So they can be much lighter, smaller than accumulators. They don't accumulate as much energy as electrical chemical accumulators, but it's enough to start engine for certain like sport cars, for certain specific application. And there, this accumulated energy of charged capacitor is used to initially rotate the shaft of the engine and started working. So that is one of the form when pure energy, accumulated energy of electric field in capacitor is transformed into mechanical energy of starting engine, and that helps to make this system much lighter and gain additional speed on the during the competition, when the sport cars are participating in some competitions. So there are, of course, much more examples, but this is one of the possible application when we don't have any additional electric circuits. It's just directly accumulator and just some electrical actuator, which converts energy electric energy accumulated in the capacitor into mechanical energy. Okay, our next topic we need to consider is capacitors with dielectrics. So far, we were talking only about two plates and consider that there is either vacuum or like can be also air. It's in terms of electrical characteristics for capacitors, there's almost no difference. But let's assume that we have vacuum, like nothing in between these two capacitors, and that's why we operate with permittivity of free space of vacuum. However, in real life, these plates of capacitors, they are not separated by vacuum. There are cases, some vacuum capacitors also, but the majority, they have certain material in between these plates. So what kind of properties this material should possess? What ideas do you have, guys? What material would you put between the plates of a capacitor? Let's say we have some glass, we have copper, like metal, and I don't know, let's say we have water. What material, glass, copper, or water, would you choose to put between plates of the capacitor if you have such a task?
Sorry, can you repeat the task? What we should
Yeah, so
like achieve?
sure. So you want, so the task is to fill the volume between two plates of the capacitor. Initially, we have vacuum there, nothing. So you need to fill with some material, and you have a choice from glass, copper, and water. Which material would you consider? Okay, there is first suggestion, water. That could be, but let's talk about this a bit later. What about other two options? We have glass and copper. Let's go to extreme cases, and then we will talk about water. Obviously, you don't want copper because copper is a metal, and if you fill space between two metal plates with another metal, you will just short it. So there will not be a capacitor, it will be just a conductor. So you will go for glass. Glass is an isolator. It doesn't conduct. If you try to measure with some multimeter resistance of glass with two wires of window glass, you will see that if this glass is dry, that it will not conduct anything. So coming back to water, it is possible to fill it with water, but in that case, it should be so-called deionized water. So first, water should be condensed, like so it's vaporized and condensed. We have so-called condensate when all impurities are left away from this water, so it's pristine water. And then in addition, it is deionized because there could be some residual ions in this water which can conduct electricity. So the key requirement for the material which is going to be used to fill the space between two electrodes is very low conductivity. So it should be a dielectric. And water can be a good dielectric only after these two steps of purification. So in theory, you can make a water-based capacitor, but again, there are some requirements for this water, because if you just grab some tap water and fill a capacitor with this, it will conduct quite a lot, because we have many like salts diluted in this water, which are in forms of ions when they are diluted in water. So they will conduct. And we use dielectrics. And these dielectrics, different dielectrics in terms of response to external electric field, possess different properties. So they respond to external electric field in a different way. Depends on the structure of this dielectric. So now let us just show how presence of certain dielectric will affect the capacitance of such parallel plate capacitor. So initially, we have a parallel plate capacitor with some vacuum between plates. So it is C naught delta V and Q naught accumulated at this capacitor. And then assume that so we detached it from the power source, from the battery, it's charged, the potential difference is delta V, and we fill this space with certain dielectric. This dielectric will possess so-called dielectric constant K. I will explain in a moment what it is. So once we put like this dielectric bulk in the space between two electrodes, and it fills completely all space, not like on this figure, but it completely fills all space between electrodes. Potential difference between electrodes will be equal to potential difference initial without dielectric divided by this K, dielectric constant. So this dielectric constant shows in how many times electric field becomes weaker inside this dielectric material in comparison to electric field outside, like external electric field, where this dielectric is placed. It shows how many times electric field will be weaker. And that's why, since electric field is weaker and difference in potential is defined as product of electric field to the distance. Distance is the same, we don't change the distance, but electric field is reduced by K. So that's why our potential difference after filling this space with the dielectric will be smaller. So for all dielectric materials, this K is larger than unity. And for free space, it's considered to be unity. That's why we didn't consider it before. So now, what will be capacitance of such a capacitor filled with a dielectric? So it will be a charge is the same. We didn't add or subtract any charge from the system. So charge will be the same. It's Q naught divided already by delta V. So this new potential difference. And Q naught divided by delta V naught divided by K. So this is expressions for delta V. And now we can write that it is K times Q naught divided by delta V naught. And this is nothing else, this ratio, as initial capacitance of this system. K times C naught. We see that by adding this dielectric material, we increase the capacitance of this capacitor filled with dielectric by K. So if we have K, for instance, 10, then we will end up with 10 times higher capacitance than it was without any filling, without like when it was a vacuum free space between two electrodes. So this is, there are two ways to increase capacitance, and that's used quite often in practice for getting capacitors with different values of capacitance. It's either to increase the electric constant of the filling of the dielectric material, which is between two plates, or reduce the distance between plates, because reducing the distance also will increase capacitance. However, it can be, if we have some requirements for voltage, like for potential difference between two plates of the capacitor, then we cannot reduce thickness infinitely, because at some point electric field will be so strong that there will be electric breakdown of the dielectric and capacitor will be damaged. But we can select dielectric materials with very high dielectric constants, and that can help to increase capacitance quite a lot. For instance, the electric constant of water, okay, is equal to 80. And that means if we have this dielectric, deionized, condensed water, like purified deionized water, we will fill this space between two plates, we will increase capacitance by 80, which is quite a lot. So there are dielectric materials, some solid state dielectric materials with larger values. For instance, titanium dioxide. This material can possess dielectric constant like 180 in certain structure. Okay, so I think for today we already are done with material. We're a bit over time. And so we considered potential energy concept, have shown that by charging electric capacitor, external agent performs some work, and this work is accumulated in the form of potential energy inside as a potential energy in the form of electric field inside this capacitor. Also, we define the specific characteristic of electric field, which is volume, so energy per unit volume of electric field, and have shown that this is only that potential energy of electric field depends as a square of electric field vector, and also have shown that by filling the space of like between of capacitor between the plates with the electric material with some dielectric constant larger than unity, we can increase proportionally capacitance of this dielectric, which is very useful in practice. And also keep in mind that there will be many problems which take into account the effect of dielectric material on capacitance of different capacitors. So this concept you should remember and take this into account when you solve problems. Okay, if you have any questions, you're welcome to ask.
Hello.
Yes.
I have a question about midterm. How it will be and when?
Yeah, midterm. We will send you soon an email with more information, but it will be on Saturday. I think it's 11 a.m. But you can check this in the manual, and we also will send an email reminding you. So it will be 1 hour. You will have certain problems. I'm not sure exactly the number, but with different complexity of the level of complexity for problems. So please be careful with that and don't repeat like previous mistakes. I don't say that you particularly did that, but in general, how you solve problems when you have limited time, like set of problems when you have limited time. You read all problems. You don't start to solve problems as they come one by one, because it could be some difficult problem and you will spend a lot of time and then you will not have enough time to solve simple, easy problems. So that's why you read all of them. You select those which you can solve in a short time. You are done with them. And once you are done, you start to consider how to solve more complicated problems. Then you will secure certain points, and will not be the case when you, instead of solving simple problems, waste all time on one difficult problem and then get very low grades. So this is my strong advice. And other from that, yeah, there will be nothing different from previous what you experienced. It will be in long kappa. So be very careful with the signs, with this decimal, the way how you represent numerical answers, with units, because the system will not accept if there is something wrong with them. Okay, any more questions?
No, thank you. Goodbye.
Thank you very much. Have a good evening and see you on Wednesday. Bye-bye.